So I left off talking about wastewater treatment. I'm going to start with a poll. So the poll is focused on what we covered on Friday. Question is, which of the following are considered preliminary treatment in wastewater? And your choices are grit chamber, activated carbon, activated sludge, primary sedimentation, and bar screens. Preliminary treatment includes grit chambers, bar screens, and equalization tanks, which I don't have listed here. Primary sedimentation is considered primary treatment. Okay, so just a little review of what we covered on Friday. So great job. So what I'd like to do today is to continue where we left off on Friday. We had been talking about primary treatment. So the goal of primary treatment is to remove the insoluble material, the particulates that settle out under quiescent conditions. So we have a problem, same theory that we've used before for sedimentation. And in this case, you have a primary tank design, and you're asked to calculate the detention time, the overflow rate, and the weir loading. So as I said, exactly the same theory that we used before. So the detention time is simply the volume over the flow rate. And you're told that the effective length is 40 meters. The width is 10 meters, and the liquid depth is 2 meters. And we'll divide that by the flow rate, and that is equal to 5,333 seconds or 1.5 hours. And typical detention times for primary sedimentation basins are from about 1.5 to 2.5 hours. So we're right within the range. So the overflow rate, as you may recall, is equal to the flow rate divided by the surface area. So that is equal to 0.150 meters cubed per second. Typically, this is given in inverse days, so we'll multiply by 64,400 seconds per day. We'll divide by the surface area, so the length times the width, and that is equal to 32 meters cubed per meter squared per day, and the typical range is 25 to 60 meters cubed per meter squared per day. And I apologize for the extra lines here. Okay, and the last is the weir loading. And again, this is the flow rate divided by the length of weir. Again, same theory that we've used before. And again, this is given in inverse days. So we have 0.150 meters cubed per second times 86,400 seconds per day, divided by the weir length, which is given, and that is equal to 173 meters cubed per meter per day, and the typical range is less than 250 meters cubed per meter per day. So we're right within the expected parameters for a primary sedimentation basin. Water has flowed then through pre-treatment, primary treatment, and now on to secondary treatment, which typically involves some type of biological processing. The goal of secondary treatment is the removal of soluble BOD. So we do get some removal, about 30 to 35% removal of particulate BOD in the primary sedimentation basin. Here we're looking at basically feeding the microorganisms. We will get some additional removal of suspended solids, but that isn't the goal. The goal is the removal of the soluble BOD. And the reason for that is that we're looking to protect the receiving body of water. If we were not to treat, then this wastewater has organic matter in it. That organic matter consumes oxygen. And what we have is the typical type of DO or dissolved oxygen depletion curve that you see here. So we have, here's our wastewater treatment plan. We're not removing soluble BOD. And what happens then is we get degradation of that organic matter, but in doing so, the organisms are consuming oxygen. And we have a depletion if we get to concentrations at or below 2 milligrams per liter. Then we have what is referred to as a septic zone. So most fish can't survive in that environment. Few can, but very, very few. We have what are referred to as sludge worms, tubifex. They are present in the sediments. Midge fly and mosquito larvae predominate. You'll have hydrogen sulfide production because you've got an anoxic condition. Smelly body of water. It's not what we want. Eventually it will recover. And eventually, long enough with no other inputs, you'd have back to a clean system. What we do in biological treatment is essentially compress this degradation process into a much smaller space and a much faster time. So we do that by ensuring that we have a high concentration of microorganisms. So process is essentially the same as what would happen in the river, but as I said, we compress it in time and space. We compress that decomposition in time and space. So the organics, we're looking to convert them to CO2, nitrogen compounds. Depending on the need, we're looking at converting that to nitrite, nitrate, and ultimately nitrogen. If we have any sulfurous compounds, we're looking at converting those to sulfate. We want to ensure that the carbon, the nitrogen, and the sulfur are in what we refer to as stable forms that are not going to consume oxygen once they are out in the receiving body of water. And we do this with a combination of microorganisms from bacteria and protozoa. Shown here, paramecium,
stalked ciliates.
We want the stable microbial community in the secondary treatment process. So in order to ensure that, when we talked back in population, the population unit, we talked about what we need to have population growth of microorganisms, and we're looking essentially at the same system. As I mentioned, we want to compress what would happen in the stream in time and space. So we need a high concentration or a high density of microorganisms. We need to have contact between the organisms that are degrading the organics in the waste themselves. We need to have organic matter that's present. And we need to have favorable temperature, pH, nutrients, and a degradable carbon source. The other thing is we need to make sure that we don't have toxic chemicals present, which is why we have pretreatment requirements. And I talked about that Friday's lecture. So when we talk about secondary treatment, there's two larger groups of treatment processes. The first is dispersed growth. So you can think of that essentially as a river. You have microorganisms dispersed in the reactor in contact with the waste. These include activated sludge, oxidation ditches and ponds, aerated lagoons, stabilization ponds. And we'll talk about these in kind of varying details. We'll have a guest speaker that will talk about oxidation ditches and the process that they're using at their plant. The second larger group is fixed growth. You can think of that as, again, think of the river, think of this rocks in the river and the moss growing on the rocks. The water flows past the rocks, past the moss, but that water is still providing nutrients to the organisms that are attached to that rock. Same type of thing. So here we have some surface. On that surface, we have our microorganisms, and the water is flowing past the microorganisms, and as it flows and as it contacts with the microorganisms obtain all of the nutrients that they need in order to grow. So these include trickling filters, biotowers, rotating biological contactors, moving bed biological reactors. And I'll add a few slides. I don't have them in today's lecture, but I'll add a few slides just to show you some of these units. So these are the aeration tanks at the East Lansing plant. They're typically operated essentially in a plug flow mode. They're very long, they're serpentine. They provide, as you can see, the bubbling. These are the oxygen diffusers right here. Organisms need oxygen in order to survive. This is a aerobic. We will do the modeling as a CSGR. It's simpler. If you stay for graduate school here, you'll take ENE 804, which is on biological processes, and you'll go through this in much more detail and the various different process operation or changes that can be made. But we'll only look at an assumption where we have a CSTR to the simplest of the model. What we have is we have flow in. We have an aeration tank. Think of X as our biomass, S as the substrate, as the BOD. So that's mixed. We're adding oxygen to it. As I mentioned, we'll assume we have a completely mixed system. Water flows then into a secondary clarifier. We don't achieve any BOD removal in the secondary clarifier. The secondary clarifier is purely for sedimentation. Okay, so that's another assumption that we're making. Now we need those microorganisms. Okay. We can't just dispose of them. So we'll take the microorganisms. Some of the microorganisms we will return back to the tank. They're our worker bees. Okay. Without them, we don't get degradation. Some we will waste. And we then have an effluent from the secondary clarifier that has a much lower concentration of BOD. This has a lower concentration of suspended solids, but the thing that we're looking at accomplishing here is the removal of BOD. Okay? The dotted line shows our system boundary, and this is extremely important in terms of the whole process by which we develop the equations that we'll use to model BOD removal. Questions before I move on? X is the microorganism. Operationally, that is what we refer to as mixed liquor. So what is in that aeration tank is referred to as mixed liquor. Volatile suspended solids. And volatile because in the test that's done, the microorganisms can be combusted, they can be burned off, they're volatile, versus the inorganics that are left behind. And then S is our substrate. So that's the BOD. So operationally, this is our BOD. Now, remember what we have, okay, is a mass balance. So let's go back. We've got our tank. This is our aeration tank. We have Q, the flow in, and the initial BOD. We have Q plus QR. Okay. Why? Because remember, we have a return activated sludge. We need to continually replace those organisms. We have a sedimentation basin. We have a flow of waste from that sedimentation basin. We have some portion that we're recycling, and we have some portion that we're wasting. Okay. We don't want too high of a concentration of microorganisms. We then have here Q minus QW, what we're wasting, and our final effluent concentration. And notice we've drawn the system boundary in this way here. Okay. And I have an extra arrow here. So, okay. So we either go this way or we. So we've drawn the system boundary around this internal loop, which is important in terms of how we develop the equations. What we have here is a mass balance between the microorganisms and the substrate. So the substrate, you can write a mass balance, okay? The substrate in the effluent, in the influent, so that's Q times S naught, is equal to, again, think about what's lost, okay? The substrate in the effluent, so that is Q minus QW times the effluent concentration plus the substrate in my waste activated sludge, so that is QW. And because I don't have any removal of of BOD in the sedimentation basin, that's also equal to S sub E plus the substrate consumed. And that's what's consumed in the activated sludge tank. And that is equal to the volume times the maximum growth rate times the substrate concentration times the biomass concentration divided by a yield rate times what we call a half substrate, a half saturation constant plus the substrate concentration. Okay, so it's a complicated equation. It's based on monad kinetics. So it's based on if we develop a model where we look at the growth rate. So we're looking at growth rate as a function of substrate concentration. It increases as substrate concentration increases and then asymptotes off. Basically, there's a maximum amount, and this is referred to this level as mu sub m. It's that maximum growth rate. You can provide more food, but it's not going to do much more for you. And at half the growth rate, this value here is referred to as the half saturation. The biomass develop a mass balance for the biomass in influent plus the net growth rate. So our substrate is being consumed, remember, but our biomass is growing. And that is equal to the biomass in the effluent plus the biomass in the waste activated sludge. Again, always look at what's entering here and what's leaving. Okay. And then what's happening in this reactor. And this is equal to Q times X naught. This growth rate is modeled with the equation here, volume times mu sub m s x over k sub s, and I'm not deriving these equations, minus kd times x. K sub d is the endogenous decay constant. And that is equal to Q minus QW times the biomass in the effluent plus QW times the biomass. And typically we use R, but note, remember, R for return activated sludge is equal to the concentration in the waste activated sludge. It's the same. This is our sludge here. Some portion we're wasting, some portion we're returning to the basin. So what we do is we couple these two mass balances. Okay. Now, I'm not going to go through and derive the equations that we move as we move forward. We'll use the equations, but I want you to know that what we've done, kind of think back to the beginning of the semester when we wrote a mass balance equation. We've done the exact same thing here. We've written, but in this case, we've written two mass balance equations. And we need to couple biomass growth to substrate consumption. And that's how we design these secondary treatment systems. All of them are based on this same premise. These equations are straight from the FE reference handbook. And as you can see, Okay, we have a number of equations that are important. Okay, the mass balance equation is what we just wrote. We have the same terms that I've used. The endogenous decay rate, the effluent BOD concentration, it's given here in kilograms per meter cubed, the same as milligrams per liter. The influent BOD, our biomass concentration in the aeration tank, we will use that as the MLVSS, a yield coefficient, which relates biomass to BOD. Remember, that's what we're linking these two mass balances. Okay. We also have a term that's referred to as the solids retention time or solids residence time. You'll also see it called the mean cell residence time. So if you think of this as how long a cell, essentially, how long this packet of cells remain in the system. Because remember, those cells are being recycled around. We have an equation for sludge volume, and then equation for what is referred to as the SVI, and this has to do with, it's a solids volume index, and it has to do with the settling characteristics of the sludge. And we have an equation that relates the biomass concentration in the aeration tank to the substrate consumption. Notice here, we've got S sub 0, the influent substrate concentration, minus the effluent concentration. Remember, we're looking at soluble BOD. Okay. Another parameter that we'll look at is what is referred to as the food to microorganism ratio. You neither want to give the organisms too much food, nor do you want to give them too little food. So if I give the organisms too much food, okay, those of you that are in the classroom, let's say you arrived in the classroom and there was a buffet set out for you for breakfast for the entire class, all 22 of students. At the end of class, what's left?
A lot of food.
A lot of food. Okay, so think about that. If I provide the microorganisms too much food, what happens?
The wastewater is not treated to the level it should be.
Exactly, the wastewater is not treated to the level it should be. Exactly right. So my concentration of BOD in my effluent will exceed the design criteria, the limits required. So I don't want to provide too much food. If I provide too little food, then I starve the microorganisms. They're unhappy and they're not going to do the job that we want them to do. So either way, we end up with problems in terms of treatment. These are the design and operational parameters for activated sludge systems. Also from the FA reference handbook. We will just look at completely mixed systems as I mentioned. But this provides you, again, with the criteria that would be used. So we'll look through a problem. We'll get through part of it today. We won't finish this. We've got a town. And this is very similar to the wastewater homework problem. So the wastewater homework problem is from chapter 23 in the textbook. I've also provided you with chapter 11 from Principles of Environmental Engineering and Science. It's shorter. It may be a little bit easier to read. Basically, Chapter 23 is a significantly expanded version of Chapter 11 from Principles of Environmental Engineering and Science. If you only read anything, read Chapter 11, and that's posted in the readings on LONCAPA. So, Town of Gatesville, it's been directed to upgrade its primary treatment plan to a secondary plan. So it's adding secondary treatment. And this is really what happened in the US. We built treatment plants that were just primary. And then subsequently, especially after the Clean Water Act was promulgated in 1972, we started adding secondary treatment. So we have an effluent standard of 10 milligrams per liter of BOD, 20 milligrams per liter of BOD, and 20 milligrams per liter of suspended solids. And we're going to, as I mentioned, we'll use a completely mixed activated sludge system. You're told that the BOD5 of the suspended solids is 33% of the suspended solids concentration. So we have both soluble BOD and we have suspended BOD that's attached to the particles. And you're told to estimate the required volume of the aeration tank. You're also given the flow rate. And you're given a soluble BOD concentration. Along with that, pilot testing would have been done, and you have the growth constants for this wastewater. So we have the half saturation constant, the maximum specific growth rate, endogenous decay constant, and a yield coefficient. So we're told again that the effluent from the secondary clarifier is 20 milligrams per liter of suspended solids. We need to determine the allowable soluble BOD in the effluent. So that's S sub E or S, just S, and depending on whether you're looking at the FA equation, or the textbook. So this is equivalent to S. And that is the BOD allowed minus the BOD 5 in the suspended solids. 20 milligrams per liter minus 0.63 times 20 milligrams per liter. And this is their suspended solids concentration. So 20 is the total. Okay. So that's our total BOD allowed. That includes soluble and suspended BOD. But we're going to have some suspended BOD because we have 20 milligrams per liter of suspended solids, and 63% of that is associated with suspended or particulate BOD. Therefore, the effluent concentration is 7.4 milligrams per liter. So that is our soluble BOD. Okay. The equation that we use then is S is equal to K sub S 1 plus KD times the mean cell concentration divided by the mean cell, I said concentration time, the mean cell residence time divided by the mean cell residence time times mu sub m minus KD minus 1. This is equation 23-14. 23-14 in the textbook. So this is S is equal to 7.4 milligrams per liter. K sub S, you were told, is 100 milligrams per liter times 1 plus KD is 0.05 inverse days times the mean cell residence time. What we're looking for is that mean cell residence time times 2.5 inverse days minus 0.05 inverse days minus 1. And when we solve, mean cell residence time is equal to 8.18 days. And this should be between 4 to 15 days. So we're right within range. Now, sorry, our MLSS should be in the range 3,000 to 6,000 milligrams per liter. We're going to use a value of 3,000 milligrams per liter. Now, typically, your MLVSS is about 70% of your MLSS. Okay, so about 30% is inorganic. So 0.7 times that 3,000 is equal to 2,100. So that is equal to X. So we're making this assumption right here. Then using equation 2023-15, X is equal to the mean cell residence time times Y. And note that was given as VSS times S sub 0 minus S divided by T naught. That's our hydraulic detention time. We have two different detention times. We have a mean cell residence time. That's what we've just solved for here, omega C, times 1 plus KD times my mean cell residence time. So that is 2,100 is equal to 8.18 days. Y was given, it's 0.6 milligrams of VSS per milligram of BOD times 84, so we said was the influent suspended BOD minus our effluent concentration divided by T naught, which is what we're looking for, plus KD 0.05 inverse days times my mean cell residence time. And I can calculate the detention time as 0.127 days, or, and I know I'm out of time here, 3.05 hours. And I'm also running out of space, so I'm going to just use this space right in here. And we'll finish this real quick. I apologize. the volume of the tank V is equal to Q times T naught, and Q is 0.15 meters cubed per second. That's what you were given. Times 3.05 hours times 60 seconds per minute, 60 minutes per hour, and that is equal to 1,650 meters cubed. So in order to solve that problem, this problem, finding the volume of the tank, we have to go through the steps using equation 23-14, 23-15, and then our definition of resonance, the hydraulic resonance time.